Okay, you guys ready to get started? Hello? All right. I like the sense of enthusiasm in here. Happy Monday to you. First off, please set up your clicker if you haven't done so already. Be ready to go today. I've got a few questions for you. Remember, it counts towards your grade now. Channel 65 if you're in here. If you're in the other classroom, it's channel 51. All right, some reminders, okay? A little bit of bookkeeping stuff off the bat. Online lifting fans learning module and quiz is due today. So it covers the lifting fan calculations we went over in lecture a week ago today, and also what you did in your skills lab last week. Please make sure you get through that. It's due by 11:59. If you log in at 11:50, I don't think you'll be able to get it done in time. Pretty positive. So make sure that you do that maybe right after class today. Rental kits are available now in the EDL. Someone from your group needs to take one for the team and go pay the cashier the $50 and find a TA. Fuel cells are included in that kit, but we are not going to give them to you until a little bit later in the semester. So just be aware, you'll get your kit minus the fuel cell for now. Journals. It's time to start logging your team's progress. Okay, so those are going to be due every week in Skills Lab. When you go to Skills Lab, the first thing you'll do is hand your TA your journal form. Okay? The form is in, I believe, the week 5 folder. So you need to start thinking about that, and we'll talk about those a little bit more. First CATME survey is due. Did you guys get an email from CATME today? Okay, log into CATME. So go there. Remember, you use your email address as your username. And you guys set up your password last time. Hopefully you chose something you remember. If not, choose forget password. But log into CATME. There's the first survey, and what it's asking is it asks about your individual or the individuals within your team and how you guys are functioning together. So you can answer honestly. They do not get, and you will not get an exact list of what people think about you, so don't worry about that. Feel free to be honest. So it tells us how you guys are functioning as a team, and it's very helpful. So please do that. It's also part of your grade. So that's that. Online safety module and quiz is due Monday, a week from today at 11:59 p.m. Lots of stuff due on Monday. Okay. Ready? All right, journals. You guys need to get a 1.5-inch 3-ring binder to keep track of your journal entry forms for the entire semester. You have one binder per team. You guys probably seen in the EDL there's mailboxes for you guys, and they're listed 1 to 108. There's 108 teams in here, so you guys have a slot. Someone needs to get a binder to keep all your stuff in. Okay. This is to document your progress and the individual efforts on the team. Okay. We know how teams work. This is helpful to you to motivate your team, your fellow teammates, and then to us to see how you guys are functioning as a team and who's working and who's not and all that kind of stuff. So please make sure you keep those up to date. You can see Chapter 1 and Appendix A in your text if you want some more information about journals. Your journal entry forms are on WebCT. They're set up for you. If you fill them out and you can see the grading rubric, do it. And it's a nice way to get 5% of your grade. I think it's 5%, maybe 10%. But they're due every week, so please start getting on that. Some more information about your journals here. You should definitely have your group contact information. So if you lose someone's phone number, you can go to the EDL and look for it. Your team charter goes in there, your calendar. Okay. Project notes, information, sketches, and research. A lot is going into this hovercraft project. I'm sure you guys are starting to look into some research online, in your textbook, maybe reading some magazines or talking to older students. All that information needs to go in your journal. That way when you go to write your paper and do your presentations or you start tweaking your design, you can say, wait, I think we might have gone down this road before. Let's go look. And you have everything in your journal. Okay. You also have your calculations, so you can review those for your tests, and also you can tweak them if necessary for your design. You have your budget and your receipts. You'll need those for your second checkpoint. And then also any helpful websites, vendors, etc. So all things pertaining to your hovercraft and your team go in this notebook. You should be able to hand the notebook to a student next semester and they would know exactly how to design a hovercraft. Okay? Questions about journals? Okay, yeah. Does it fit in the male slot? I would prefer if you can find a 1.5 incher. They'll fit. Maybe use that for another class. Thank you. That's a good question. Please make sure your binders will fit in the male slot. It'll make it easier for you and your TA. Anybody else? Okay, moving forward. We go one too far. This is your journal entry form. Okay. So again, submitted every week. This is a grading sheet. You guys know exactly how you're being graded in this class, so make sure you're doing what you need to do to get the full amount of points. And you guys can review this more online. I'm not going to talk too much about this. And then along with your journal is a work distribution form. So you've got task name, task description, and team members participating. And then down here is everyone's favorite, team member, % contribution for this period, for that week, and your signature. Okay? This is what keeps you guys honest with each other. Right? If you say you're going to do something, make sure you do it. Be a good team member so people want to work with you for the next 4 or 5 years. It's a lot nicer to get through engineering school when you have friends to work with on projects. So anyway, so the work distribution form, again, that goes with your journal. So make sure you guys get that in too. So you can add up the percentage to 100%. If there's 4 of you, you can get up to 25% each. Some weeks you may do more, some weeks less. Who knows? Okay. All right. Continuing last class, we seem to be, I guess Dr. Lacombe and I are chatty because we keep going over time. To continue with batteries here, I'm going to talk about those briefly, and then we're going to move on to circuits. But things to consider with your batteries are weight, voltage, current capacity. Are they rechargeable or not? You don't want to go through a ton of money in this class. Remember, every last battery goes in that budget. We don't want you to spend a ton of money. Okay. Types of batteries, you guys discussed the different types on the market. Okay. Some of them we discussed probably aren't affordable, but we want you to be aware of what's going on and in battery technology and what's available. You need to know how to read your fan data sheet because we need to know how much power those fans take and what their voltage requirements are and their amperage. We need to know about parallel, wiring batteries in parallel and series, and I'll get to that first. I think you guys briefly touched on it. I'll try and recap it a little bit today. And then you have to use battery packs, not battery holders. They catch on fire, and we don't want to burn down the EDL. It's a gorgeous new lab we have, so let's not do that. And then we need to talk about discharge rate of batteries. So these are all things you guys covered briefly. I'm going to recap it with a couple slides, and then we'll move on to new stuff. Any questions before we, yeah? How they could melt them? Weld them. So a lot of students will go to Batteries Plus, and they'll package them for you in series. Are you asking if you want to do it yourself? What's that? Yes, that's allowed. Yeah. And we can talk more after class too. But you can go to Batteries Plus and get your batteries put in a pack for you. That's nice. Take care of it. Anybody else? All right. Okay, so batteries in parallel. When you wire batteries in parallel, you are adding up the amperage. So you're increasing the life of the batteries. So I like to remember this. Parallel has 2 A's in it, so adding amps. It increases the life. So if we have 4 batteries here that are 1.2 volts, and it looks like 1,000 milliamps each, if I put them in parallel, which means I connect all the positives and I connect all the negatives, I can add up 1,000 milliamps plus 1,000 milliamps plus 1,000 plus 1,000, I get 4,000. So if you wire batteries in parallel, you're adding up amps. And amp hours, that tells you you're increasing time because hours is in there. Nice mnemonic device to remember for that one. Okay, so you're connecting all the positives together and all the negatives when we're talking about batteries in parallel. All right, if we go in series, okay, we're boosting the voltage. So you guys are asked to find 12-volt fans, approximately. So a lot of batteries are 1.2 volts. I think you guys talked about the AA's. So we got to get up to 12 volts. And the way we do that is we put them in series. We showed you the battery packs that you're not allowed to use. Okay, those ones are the plastic ones that melt and start fires. Or you can, again, go somewhere and have them wrap them. But when you wire them in series, you're adding up the voltage. So here are my same batteries. They're 1.2 volts, 1,000 milliamps. I get, oops, sorry, 1.2 volts plus 1.2 volts plus 1.2 volts plus 1.2 volts, or 1.2 times the number of batteries. Okay? So my volts is all adding. So if I put these 4 batteries in series, I'm getting 4.8 volts. But my milliamp hours stays the same. So it doesn't buy me any time. It just gets me to the voltage that I need. Yes? If he asks, what if all the batteries are 2300 and then one is 1000 or a different, it adds up in parallel. In series, I believe you would get, that is a good question. I'm not quite sure the answer to that, and I can look it up for you, but I think you would get the 23, I think you'd get somewhere a little lower than 2300, but I'm not sure. It might go to the lowest denominator. Let me look into it, and I'll get back to you. Come see me after class so I can write down your email. Okay. Anybody else? Questions? That is an excellent question. All right, so series, we wire positive to negative, positive to negative, positive to negative. There's some clicker questions coming, so keep that in mind. Parallel, okay? You do all positives and all negatives wired together. Series, we go positive to negative and positive to negative. All right, so your first clicker question, and I will start it this time, I'll remember. Are these batteries connected to the fan in series, parallel, or both? And I know I'm getting it. There you go. Oh, sorry. There you go, more time. $20 seconds. Are the batteries in series, parallel, or both? Four, three, two, one. Good job. The batteries are, in fact, in series. Yay. Okay, they're in series because you have your positive end wired to your negative end. Okay, positive to negative is series. Good job, you guys. All right. Battery holders come in many shapes and sizes. Okay? These battery holders put batteries into series for you. Remember that series is, again, it's increasing the voltage. So you're going to have to get batteries in series in order to get to the voltage that you want. You cannot use these for ENGR100. Again, for the 3rd time today, do not buy these cheap plastic battery holders. They melt, so don't use them. Okay, an example calculation. You chose a fan, and the fan's flow rate is 95 CFM. The voltage is 12 volts, and the current is 1100 milliamp hours. Okay, so those are your fan specs. You looked up your fan on the data sheet, found that out. Next, you go and you choose batteries. And you chose standard AA cells, nickel metal hydrides. You have a voltage of 1.2 volts per battery and a capacity of 2,500 milliamp hours. So the first question is, how many batteries do you need? So to do that, we do one simple divide. We take our 12 volts required for the fan, and we're going to divide it by 1.2 volts per battery. So here you'll see your volts will just cancel out and batteries come to the top. Okay? And you have 10 batteries. Pretty easy calculation, 1.2 volts per battery, and you know you need 12 volts. You need 10 batteries. The question is are those batteries in series or are they in parallel? Yay, series, good. You guys are so smart. Okay, next up. Anybody have questions about how to get voltage or batteries? Okay, so capacity. If I have 2,500 milliamp hours, okay, that was the capacity of my battery, so one battery, and my fan is going to take 1,100 milliamps. I can divide those two numbers and cancel out my milliamps, and I end up with hours. So my capacity is going to be 2.2 hours. So these 10 batteries will last me 2.2 hours for my fan. So this is just for one fan. What happens if you power 2 fans? Time goes down? No? Oh, yeah, time's going to go down. We're going to talk about it. We're going to talk about wiring fans in series and parallel and how that affects your batteries. Okay. This is true. He said it's only if you're using the same batteries. We'll talk some more. Yes? Hold on, can you repeat yourself? This one or this one? The 1100 milliamps was the capacity that the fan was rated it needs to run. Yes, it is a typo. Thank you. Yes, thank you for catching that. This should be 1100. Sorry about that, you guys. The numbers should match. Good catch. I didn't catch it today. Okay. Anybody else? All right. Another example. Most of the times when you look at your fan data sheet, it's going to tell you the power and the voltage, but not the amps. So we just need to do a simple thing here. Current is equal to power divided by voltage. So I take my power, my 100 watts, divide it by my volts, and I get my amps. Once I'm in amps, I'm going to convert to milliamps because typically that's what my batteries are going to be rated as. So all I did was took my current and set that equal to my power divided by my voltage. So now I'm back to what we just did, where we're looking for the number of batteries. The number of batteries, we take the volts that our fan requires and divide it by the number of volts we get per battery. Okay, 10 batteries. In series, you guys got that down pat. And then our capacity, looks like I don't have a typo here, so that's good. The capacity is going to be the 2,500 milliamp hours that your battery offers, divided by 8,300 milliamps that my fan requires. So this one gets me about 20 minutes. Be a bigger fan. Got a few people writing. Anybody have questions? Yes. Excellent, excellent question. He said, if you have battery packs in series, can you wire them in parallel to get more time? Yes, you can. That's what you're supposed to do. Great. Good job. And we are going there today in class a little bit, and then in lab this week. You guys are going to do an experiment with different battery packs and fans. Okay. You guys good? Anyone need a moment? No? Okay. All right, question 2. Are these batteries connected to the fan in series, in parallel, or both? And I'm going to start the poll, and I'm going to move this. This is a battery pack, and this is a battery pack. No, it's a pack of batteries. If I answer too much, I'm going to give it away. Whoop. Oh, 30 seconds. That went fast. What did you guys choose? Both. Great. So let's look at this here. Okay. Each battery pack has 8 cells in it. Each battery is a cell. Okay, so we've got battery packs wired in series. Okay, the 2 battery packs are wired together in parallel, just like we had the question down here. Okay, so it's both. The batteries are in series. The packs are wired together in parallel to the fans. So that means that we're getting up to the voltage we need, and we're increasing the time that these batteries are going to last. Yes? The battery packs, anytime you have one of these plastic packs, they're in series. The way these packs are constructed is that it's connecting the positive to the negative terminals. So that's like, this is a picture of the plastic ones that we say don't use, but they're in series. It's just like if you open up your remote and you see the 2 batteries in there, those are in series, sort of thing. Okay. Question? not that I have seen, but you wire them together in parallel is how it works. Yeah. Good question. Yes? Sorry. Back here and then, yeah. What's the math on this? Good question. So he asked, what's the math on these packs? So what we will do is, when they're in series, we're adding up the voltage. So we have 1.2 volts times, it looks like 8 batteries. Okay? So this has, what is that, 2.4, 4.8, somewhere around 10. So the volts are both the same in both those packs. When you wire them together, all you're doing is you're wiring them in parallel. Remember, in parallel, we add amps. So you're taking the milliamps of one battery and adding it to what's available from one other battery. He asked, are you getting the best of both worlds? In my opinion, yes, because say you need 12 volts, so you wire 10 batteries together to get to your 12 volts. When you wire that pack in parallel to another pack, now you're doubling the time you have available to run the batteries. Okay. Question? The voltage, this voltage right here, once you add them up in series, that's going to be constant. So when you wire it to this other pack, the voltage will not change. The amps increases. What you have to remember is that when you wire in series, and that's what this pack is, that's when you're adding up voltage. Once that pack is series, you get to the voltage you have, you're done with voltage. You wire it to this one, and the only thing you're adding when you go in parallel is you're adding up amps. So that's where you're increasing the amps. And the voltage stays the same. In parallel, voltage does not change. Does that get you? Okay. Anybody else? Oh. You have to know the in series. So you can see that they're in parallel. Well, you know, I was hoping you know they're in series because they're in a battery pack. So maybe I didn't make that clear earlier. If you have batteries in these black packs, they are in series. Okay. Sorry about that. I'll take blame for that one. Yes, back there? Yes. If one pack had 2 batteries, was missing 2 batteries, if you only had 6 batteries in here, then you'd only get 6 times, say, 1.2 volts versus 8 times 1.2 volts. Just the voltage. Your amps won't change. What would change the amps, if these packs weren't wired together in parallel, then you wouldn't change the amps. They would stay the same. Who else? Anyone? Yeah. Yes. Good. He's got a great question. He said a lot of times when you buy batteries, they're rated at a certain voltage, but you're not actually getting that voltage out of them, which is very, very true. So do you add more batteries, or what do you do? So, yeah. My understanding, what I would tell you is, you want 12 volts. I would design enough batteries to get to 12 volts. I would know in my design, remember design is an iterative process, so things are always changing. You probably overestimated on your weight a little bit. You may have overestimated on your CFM a little bit. So if your fans are running a little bit slower than 12 volts, say, then I think that's okay because they're going to be constantly losing power. So let's overestimate on the weight and the CFM you need and stick to 12. It's very complicated because you'll find this process is very circular, hence the iterative process. Because you choose batteries and then 10 minutes later your batteries are losing power and your hovercraft's not floating as high as you want, et cetera, et cetera, et cetera, and it keeps going. So you kind of got to draw the line and choose where you want to design around. I like a little safety factor, so I would go over on the weight and a little over on my CFM. Because you can always add weight or whatnot. Okay, anybody else? All right, keep going then. All right, so the discharge rate. This kind of goes along with the question. You guys are prompting my slides. I love it. You are interested in the discharge curve. We tend to hope that batteries will provide the rated voltage until they die. Like you'll have 12 volts and then instantly it's just dead. This is not how life works. So most of them are going to lose their rated voltage pretty quickly. So you're going to design around 12 volts, but the reality is you're going to be at 12 volts for 5 or 10 minutes and then you're done. Well, not done, but you're not at 12 volts anymore. So here's a discharge curve. And you'll see up here in this first, that looks like about 1 minute over here. You guys can see. For about 1 minute, you're getting a little over 12 volts, okay, 13 to 11. And then it drops off. The less amps that you're requiring, you'll see this is a little steadier here at 3 amps. Okay? And this is time down on the x-axis. The less amps you're requiring, the longer you can keep it at 12 volts. But the more amps you need, the quicker they discharge. So, and you'll see some of these drop off really quick. Over here at 165 amps, you're getting like 5 minutes out of that. So make sure that when you choose batteries, look at the discharge curve and make sure it's going to function as you need it to. Heidi, do you have? Good question. She asks, is that regardless of whether they're in series or parallel, or is that just strictly series? This is just a battery in general. It doesn't matter how you have it wired. One single battery. Yeah. Does the rate change the more you charge the battery? Yes, it can. It depends on how the memory effect in the batteries you choose. I know you guys discussed briefly last week about memory and things like that. You want to choose a battery that doesn't have too much of a memory problem, or you will start losing your charge capabilities. Anybody else? Yes, sorry. I believe that is not a good idea to wire them together, the different chemistries. We can talk about it some more though. But yeah, I don't think that's advisable. Okay. Anybody else? All right, moving forward. So those are some battery basics. Hopefully your mind is jogging now as to what to do. The one thing I ask as we go into this is remember what series and parallel are, because it's going to come back again here in a minute. But relays and basic circuits. This is going to be a brief intro. We have about 20 minutes left of class. This week in Skills Lab, you guys are going to be going over circuits. You guys are going to be wiring up fans to battery packs and trying different configurations, and you will see what I'm talking about, which will be really nice. Okay. So you guys have that coming at you, and then also you guys are going to be working on your circuits in lab. So here's some basic information for you. All right, so we need to talk about circuit components that we're going to be using in this class. So some basic circuit components, series and parallel connections of fans. So series and parallel hasn't gone away. We're going to talk about soldering briefly. Has anyone soldered in here? You guys? Oh, good. Lots of you guys. If not, you will solder in class. We need to talk about breadboards versus strip boards, and then switches and relays to control power. So lots of stuff. I'll see how far I can get. All right. The components that you will be using for the most part in here are resistors, okay, which is your fan, wires, a switch or relay, and a source of energy, so a battery or your fuel cell. So a resistor is any conductor, which in this class it's a wire, okay, warms up while conducting electrical current due to the collision of electrons and atoms. And sometimes we want to slow down the ability of those electrons to move, or just when we plug something into our circuit, like say our fan is a resistor, and that slows the flow of electrons. Okay? So it's known as resistance, because it's resisting their movement. You can think about it in terms, when you guys read chapter 4 in your book, I think that's your reading for the week, it talks about all the different electrical components in terms of water. And this one talks about resistance in terms of pipe. It takes a lot of pressure to force water through a small diameter pipe, versus if you have a huge pipe, water flows pretty readily. So the higher the resistance, think about the smaller the pipe, the more pressure you need to force your electrons through or force water through. And this is governed by the equation. It's a classic equation. It's Ohm's law. Some of you guys may have seen in physics this week or in high school. Voltage is current times resistance. V equals IR. Don't forget that one. We're going to use that all day today and all semester. V equals IR, where V is voltage and I is current. I know current seems like it should be C, but that's capacitance, so V equals IR. I is current. V is voltage. R is resistance. All right, so the unit of measure of resistance is ohms, and it's named after a German physicist, George Simon Ohm. Okay. And here's the equation for you. Resistance is equal to rho, nice little Greek letter, and that's the electrical resistivity of the material measured in ohm meters, and it's a constant depending on the material we're talking about. So that's something you can look up. A is the cross-sectional area of the conductor. Again, the conductor is your wire. And L is the length of the conductor in meters. So resistance is rho times L over A. Mostly today we care that V equals IR, to be honest, but this is good to know. Okay? And it's measured in ohms. The unit of measure for resistance is in ohms. All right, so an example circuit. We have a resistor R, and that's represented with a bulb or a fan. In this class, that's going to be your fans. Okay, and you have a wire connecting everything together. You've got a switch turning your circuit on and off. That's making sure that your battery is connected so that you're getting power. And then you have your battery, which is your source for voltage. So this is maybe the first time you've seen a circuit diagram. So what this means here, I've got these little circles are showing up, these green circles. Okay? Those are nodes. And that's just where things are connected together. And on your circuit, there are these points. Okay? So just so you know. Right? Terminal voltage is how much voltage you're putting into the system. So what are your batteries rated to? Sorry, go back. Okay. So this is the basic circuit. So we have our voltage. You guys remember this sign for a battery? Okay. Current I is going through here, and here's our resistor R, which is going to be a fan in this class for the most part. Okay. And the door here, it looks like a little trap door. That's your switch. So when it's open, right, the voltage can't go through. You close it, and then it's a closed system, and your voltage, your battery power can go through the circuit. Okay. So here's same thing. And as I told you before, V equals IR. Your voltage is equal to your current times your resistance. And so we can do a little bit of algebra, and we find that current is equal to voltage over resistance. Okay. So a note to you. Each conductor or wire has its own internal resistance, and it's very, very, very low. The load, like if you have a toaster or a light bulb, your fan, whatever it is, has a lot more resistance. Right? It's harder. It's really restricting the flow of electrons because it needs power. The current flowing through the circuit, though, is extremely lazy. Okay? Really lazy. And it's going to take the shortest and least resistive path to complete the circuit. So if you accidentally wire in an extra wire and you what's called short circuit your load, okay, those electrons are lazy, lazy, lazy. Okay? Sunday morning lazy. They are going to take the least resistive path. And what happens is, when that happens, okay, your resistance goes way down in your equation, V equals IR, which causes a shoot up in your current. And when that happens, you are going to get smoke coming out of your circuit, and you'll have to redo it. So please make sure you do not short circuit your load. And we will build circuits in class, so don't be too alarmed. So remember that electrons are lazy. Wires are the least resistive path. All right. So back to this whole series and parallel thing. Now we're talking about, before we were talking about wiring batteries in series, now we're going to talk about wiring fans in series. So this R1 and R2 at the top here represent fans. Okay. V is going to be your battery power, so your voltage, and you've got your I, your current going through. When two resistors are in series, the current flowing through the resistors are the same. The current doesn't change. Remember in series, current doesn't change in batteries? So you can kind of draw some parallels there. Shouldn't use that word probably right now, but series. Okay? Current flowing through the resistors is the same. If the resistors are identical, so if you have two of the same fans, they have the same power requirement, same amp requirement, same voltage, the voltage across will be half the source of the voltage. So what happens here, you guys can look at this in math terms. You've got voltage is current times resistance. In your book, you can see the entire derivation of this in chapter 4. You'll see it in your reading this week. R equivalent is R1 plus R2, so you add up the resistance of those fans. If current is to stay the same, and you keep adding in fans in series, so you have R1 plus R2 now, voltage has to go down in order to keep I the same. Right? You keep adding in there into the denominator, something's got to give. And if current stays the same, then voltage will go down. Makes sense? Because if I add R3 in here and R4, right, that denominator is getting bigger and bigger, which means my numerator needs to get smaller. Yeah. Will the wire ever resist the voltage? If you hooked up your circuit wrong. Maybe. We'll walk you through it. We'll help you out. Yeah. Okay, so current is going to stay the same in series. Okay? Keep that in mind. If we put two fans in series, the voltage goes down. So what happens if the voltage goes down to these fans? Then what are we getting? They go slow. They become sluggish. Okay? They're on vacation. Okay? So if you put two fans in series, you're cutting the voltage that goes to them. Probably don't want to do that, depending on what your design is. Okay. Clicker question. I hope I've prompted you well this time. Connect two identical 12-volt fans in series, and you're powering them using a 12-volt battery pack. Remember, V equals IR. The voltage across each fan is either 1, 24 volts, 2, 12 volts, 3, 6 volts, or 4, 3 volts. Hop to it. Four, 3, 2, 1. Yay, good. Good, good, good. 6 volts was the determined factor in here. All right, way to go, class. You guys are... Okay, if you want more explanation, R1 equals R2. We said that the fans are identical, okay? V1, V equals IR, remember that equation hopefully, is equal to I1 times R1, and V2 is I2 times R2. Okay? Simple formula. We said the current stays the same because they're in series, so I1 equals I2. And therefore, and we can say that, we can sub in here, if I2 equals I1 and R2 equals R1, then we can say that I2, R2 equals I1, R1. This is up later if you want to look at it on your own time too. So V1 equals V2. Okay? So V2 equals I2, R2, which equals I1, R1. A little bit of circular logic, and you'll come up with V1 equal to V2. So going from there, the total voltage is V1 plus V2. And if I change my V2 out for V1, then I get voltages V1 plus V1. Okay? And I have 12 volts. And so V1 equals 6 volts. Okay? You guys did really good on that. Good job. Anybody questions? Okay, moving on. All right, so just as you can wire fans in series, you can also wire fans in parallel. Okay? So these are two fans in parallel, drawn a little bit different. They're parallel to each other. That gives you a good indication. We've still got the one voltage source, the current going through, and there's a trap door up here, right? That's our switch. So when we close that, this is when power gets up there, okay? The door up here. So when two resistors are in parallel, so your two fans, okay, the current flowing through the resistors are the same only if the resistors are identical. So you have to have two identical fans. The total current is the sum of the currents flowing through the resistors. And the voltage will be the same as the source voltage. And the way you can remember that, again, remember back to batteries, in parallel, voltage stays the same. So here, if we put our fans in parallel, our voltage stays the same. Okay? So the voltage going to these fans, if they're in parallel, will be the same. The current is what changes this time. Well, it doesn't exactly change. but it's affected by how many fans you have. All right, so V equals IR equivalent again. Your R equivalent, I did a little math here. Again, this is in your textbook, chapter 4. Okay. You have R1, R2 over R1 plus R2. And you have your current, I is equal to I1 plus I2. Sorry, I'll go back. Okay, so two fans in parallel, they will get the same voltage. So if you have fans that are 12-volt fans, if you wire the two fans together in parallel, they will both get 12 volts. What happens is that the current splits between them. You have a total current I, and that's the equivalent of I1 plus I2. So you have I1 coming to R1 and I2 coming to R2. So the current, remember, is measured in milliamp hours. So what that basically is saying is that you're getting less time with more fans. But you keep the voltage the same. Yeah, Heidi? Yes. She asked, does it work one way? I don't know. You're asking how they're wired, I think, essentially. How are they wired together? You wire fans in series and parallel the same thing you do with batteries. Remember in series, you go positive to negative, positive to negative. Same thing with fans. If you were going to wire fans in series, you take the black wire to the red wire, or negative to positive, however you want it. If you are going to run them in parallel, then you put together all the black wires and all the red wires of your fans, and those go to the battery packs. And you guys will be doing that in Skills Lab this week, so you'll get lots of practice. Hopefully that'll help clarify things. Okay? Anybody? All right. So your two main circuits you're going to be using in this class are the first one here, your lifting fan circuit. You have the voltage of your battery pack, so 12 volts. R is your lifting fan, so you've got two fans. Okay? So you'll probably have two, maybe three fans, depending on what size they are, for lift. And those will be wired in parallel. So this will be one circuit. Your second circuit will be based on your fuel cell. Okay? The voltage of your fuel cell is about 3 volts. And then your resistance is probably going to be a motor, but it depends on what you guys design. But the fuel cell circuit you guys see below is the first one we talked about today, where you have a voltage, a switch, okay, turning that fuel cell off and on, and then your fuel cell. All right? Basic circuits. Okay. So, soldering. It sounds like, or looked like, a lot of you guys had soldered stuff. That's really cool. Most common electronic solder is 63% tin and 37% lead. Okay? Lead is bad for you, so please wash your hands and don't eat the solder. It's not good. Joking. I don't want to give anyone ideas. Solder melts around 360 degrees Fahrenheit. That is very, very, very hot. It hurts if you touch it to your hand. Okay? You will wear safety goggles because you don't want to stick a soldering iron in your eye or anything else. Be careful with these. It sounds funny, but I burn myself at least once a year with a soldering iron, and it hurts. So please don't do that. Avoid burns from the soldering iron and then from flying solder. You'll find it pellets off in little balls, and it goes everywhere. Be very careful with it. Avoid breathing the smoke. Again, it's got lead in it. It's not good for you. So don't breathe it in. Don't put it in your eyes. Don't swallow it. Should be good. Wash your hands. Okay? You guys have, I think there's a soldering iron video up for you guys, and you guys will do that again in lab. So everyone will get a solder. You guys are going to use a strip board or a proto board, it's called. These are used for small electrical circuits. So you guys are going to make a small electrical circuit in order to run your hovercraft. Okay? It'll have wires, relays, switches hooked up to your fans and your batteries. The electrical components have to be soldered on these. There are breadboards that have electrical conductivity, but in here we want you to learn how to solder and put things together, so we are going to use these. They are in your kit for you. You have a couple choices to control power. The first is a switch. Okay, you get both of these in your kit. A switch is a mechanical device to connect or disconnect the electric circuit. So you can see up here on the top right. Okay, it's got an I/O on-off switch. Pretty familiar with those. So you guys can use those probably for your main power to your lift fans or something like that. So when you hit the switch, your hovercraft lifts. Is the idea. The other thing you guys are going to have is a relay. And a relay is an electrical switch. So the first one is mechanical. You're touching it. Okay? A relay is an electrical switch that opens and closes under the control of another small-scale electrical device. And you guys are going to use the NXT. And the NXT can do what we call throw relays. And it basically opens or closes one of those trapdoor-looking things on the circuit. Both are included in your rental kit. So with the NXT, you could say, oh, my light sensor said this, so I want this to happen, and that's what you use your relay for. Relays, typical control voltages of a relay are 5, 12, 24 volts, 120 volts. I believe your guys' are 5 volts, and they're in your kit, so you don't have to worry about it. Typical current limits are up to 15 amps, and it's basically got a low current electromagnet that's energized to throw. Okay? So we can watch this video here. Okay? See this blue door, it's opening and closing. Your NXT is going to send a signal, right? And as this door closes, you'll see my light bulb lights up. Really cool little cartoon. Isn't it exciting? So this is what a relay does. It's basically, an electrical switch that when you tell it, when another circuit tells it to close, then it provides power to your circuit. Okay? So you can use your NXT to do this, and we will show you how in Skills Lab. But it's only on-off. Okay? So here's another, just a diagram for you guys to look at. You have your NXT, okay? And it's going to send a signal, and when it gets to this right here, your door, your relay, that gets thrown. That little trap door closes, and your fans, okay, and motors, everything's all connected and ready to go, depending on how you wire them. Okay? So something else we'll do in Skills Lab. Yay, I actually got through the whole lecture today. We're caught up. Take-home points, real quick before you go. Thank you. Resistance. Fans are modeled as a resistor. Voltage is going to it's supplied by your battery packs. Okay, you need to worry about current and voltage, series and parallel. Study up on these things. Okay, have a great week. We'll see you guys Wednesday.